hear me now? Cool. The way I connected is not giving me control of the settings. Yeah, I can turn on the closed captioning. But at least I'm connected. Oh, here we go. Closed captioning. On. All right, I can record. All right, let me start the recording. All right. So our quote for the day: education is a progressive discovery of our own ignorance. And that is from Will Durant. All right, so hopefully you got the study guide open last night. I didn't open it at 11, and like I said, I tried to. I was playing a game with a friend of mine and didn't get done until after midnight, so I think I turned it on after midnight. But should have seen it this morning. We'll see it. That's the study guide. Those are the topics that will be on the exam. We're going to go over some of those topics very briefly today to hopefully give you a better chance to make a good grade on the exam. And hopefully that's positive, something that will happen. Now, to make the best grade on the exam, you need to be reading the book, each chapter as we go through, taking notes on the bolded items, and then listening to the lectures and maybe adding to your notes of what you did in the book. Maybe something I talked about, that thing that wasn't wasn't something you wrote down from the book. You write that down then, and then when you get the study guide, you've got most of it already done. You maybe look at it a little bit more to see if there's anything you missed, but most of the work is done by that point, and so you don't have a lot of work last. If you haven't done that, it's a little harder. You got to do some more work. But let's go through chapters in order with the topics that are going to be on the exam. Now, I went through and I highlighted a lot of the topics. I think all of the topics that are going to be on the exam, but I may or may not have missed one or two. I think I'm going to cover everything, but you got the study guide, and that's going to have 99 to 100% of everything is going to be on the exam. Right? Maybe one or two things not on the study guide that should be on, but I haven't found them yet. So, chapter 1. All right. So we have the components of a network. Components of a network. All right, so The components of a network are server, client, and circuit. So circuit is what connects everything. That's the cabling that connects everything. The client is any computer that is requesting services of a server. Usually, it's a PC, like a Mac or like this Mac or that Windows or a Linux computer. Those are the stereotypical clients, but it could be any computer. It could be another server. It could be a mainframe. It could be a supercomputer. Any computer that's requesting services of the server is a client. Okay. And then the server. The server is a very powerful computer that does one thing. Okay. You have an email server, right? All it does is do email. You have an internet server. All it does is send web pages and the components of web pages to people who request it. You have a print server that allows people to print at whatever printer they want to, right? So say I had a printer here in the corner. If I wanted to print to it, I would send a print command, but it would not go directly to that printer. What it would do is it goes somewhere on campus to wherever the print server is, and then the print server would redirect it here. Why would we do that? Why does it have to go all the way across campus? Probably in this building, but why does it have to go all the way across campus to send something there? Well, that way we don't have to have a cable running from that printer to my computer. If I wanted to send it directly there, I'd have to have a cable, right? But if I want everybody to have the opportunity to send something to that printer, then we need to have a print server. Right? That way we can share resources. That's what print servers are for, sharing the printers, where everybody can send something to it, right? So we've got lots of different kinds of printers. Those are servers. Those are some of the kinds of servers. We have application servers, storage servers, all kinds of servers that are possible, but they do one job for thousands or millions of people. All right. Then we have types of a network. A little cursive in there. Hopefully you understand. You don't know cursive. Types of networks. We have personal area network, PAN, local area network, or LAN, metropolitan area network, or MAN, and wide area network, or WAN. So what do all those have in common?
Area network.
Area networks. Then we have backbone networks, and we have two specific kinds of backbone networks. We have a building backbone that connects everything in a building, and we have a campus backbone that connects all the buildings. But for this, we haven't got to that part yet about the two different kinds of backbones. So at this point, it's just a backbone network. Okay. Now the backbone network is not an area network. It's more like a superhighway. Right? Lots of information traveling down it to connect everything. Right. All right, then we have the categories of networks. All right. So we have the internet or internet. The internet is a network of networks, and it is public. So it is a public network of networks. Right? That's what the internet is. Internet. The intranet is a company's internal private network. Right? So the intranet is a company's internal private network. The extranet is also private and is connected to the intranet. That allows vendors and suppliers to log into the extranet, verify their identity, verify that they are authorized to connect to the intranet, and then they can connect to the internet. That's where Sally's Jellies can log into Walmart's extranet, and then that connects to Walmart's intranet, and then they can see how much of inventory Walmart has of Sally's jellies. If we need to make some more because they're going to order pretty soon, right? Something like that. So the intranet and the extranet work together, and they're both private networks. All right. And then the 800-pound gorilla in chapter 1, the OSI model. Right. Several questions on the OSI model on the exam. Several. Right. And in fact, there'll probably be questions about the OSI model, various parts of the OSI model on every exam, including the final. Right? It's because it's so integral to everything in networking and in any kind of network, including the internet. Right? So we have 7 layers. First layer is the physical layer. The physical layer has the cables and the connectors and all that kind of stuff. And the data at the physical layer is just binary, zeros and ones. No PDU, just zeros and ones, stream of zeros and ones. Data link layer. The data link layer has error checking and does a little bit of traffic cop stuff, and that's where the switches and the hubs are at. Switches and hubs are at the data link layer. And the PDU at the data link layer is the Ethernet frame. PDU is protocol data unit. The PDU, protocol data unit, sometimes called packets by old people like me, but the PDU is how we separate the data into little chunks of data and then wrap information around it to send through the networks. That's every time it gets a new layer, it gets a new name for the PDU. So at the first layer, data link layer, the name of the PDU is the Ethernet frame. Now, the next layer, networking, or the network layer. The network layer does the routing. That's obviously where the routers are, right? So the network layer has the routers, and the PDU for the network layer is the IP packet, Internet Protocol packet. Okay. That's why we call the bundle of data we're sending a PDU instead of a packet, because we got an IP packet, and it's confusing. Right, so they changed it to PDU. Right. So the IP packet, obviously the IP protocol is also at this layer. I'm dealing with the IP packet. So the Internet Protocol is also at the network layer. Transport layer. Transport layer has the start and stop flags to let you know when the PDU begins and ends. Right, when each PDU begins and ends. It does a little bit of error checking. And the transport layer has the TCP segment as its PDU. So obviously that's where the TCP protocol is. Its mission control protocol is at the transport layer. Session is the next layer. Session has login information, file transfer, security, does accounting, all kinds of stuff. Doesn't really have a PDU for that layer. Just call it data at this point. We'll talk about what happens in a minute. And the presentation layer. Presentation layer, where the operating system is. This does the input and output, data compression, screen formatting, all that kind of stuff. And it is also data. It doesn't have its own PDU. And then we have, finally, the application layer. 7th layer is the application layer. And the application layer has the utilities, the network monitoring, management, but it also has programs like your browser, Microsoft Outlook for your email system. All of those kinds of programs are at the application layer. And it also has data. Now, if you take the 3 layers that have data, that don't have their own PDU, and you put them all together, you actually get another PDU. And that is the HTTP packet, Hypertext Transport Protocol packet. So obviously, we use HTTP at this layer, these 3 layers. Now, they've actually got some acronyms to help you remember the different layers and the order that they're in. The 2 that I like, I mentioned in class before, but I like them. Please do not throw sausage pizza away. Right? So please, physical, do, data link, not is network, throw is transport, sausage is session, pizza is presentation, and away is application. So please do not throw sausage pizza away. It's a quick, easy way to remember the layers in order. Right? Another good one is please do not tell secret passwords anytime, which is also good advice. Right? So please do not, please do not tell secret passwords anytime. So that's another acronym to remember, the OSI layers, 7 OSI layers. Right? Then we have the internet model. Now, the internet model only has 5 layers. The first 4 are the same as the OSI model. Okay? So you have the physical, data link, network, and transport. Those 4 layers are the same in the internet model. Now, the last 3, session, presentation, and application, are all combined into an application layer. So the 5th layer on the internet model is application layer, and it's kind of a grouping of the last 3 layers of the OSI model. Session, presentation, and application. So basically, session and presentation are merged into the application layer for the internet model. Right? Which makes sense because all 3 of them together give you the HTTP packet. So it makes sense that they get merged, in the internet model. Then we have groupings. So application is already kind of a grouping, and we add that to the groupings as well. But then with those 4 layers that are left in both the internet and the OSI model, we take the first 2, the physical and the data link, and we group them together, and that's called the hardware layer. That's where most of the hardware is, the hardware layer. And then the next 2, the network and transport layers, we combine them into a group, and that's called the internetwork layer. Remember, internetworking was the protocol that people on ARPANET figured out how to combine networks of different kinds together, which created the internet. That's where we get the term internet from. Right, so internetwork layer or network grouping is the network and transport layers. So we have the hardware layer, which is physical and data link. We have the internetwork layer, which is the network and transport. And then, of course, the application is the session, the presentation, and the application. All right. And that is chapter 1. Now, it's not a lot of topics. So what does that mean? If there's equal number of questions in each chapter on the exam, roughly equal. If you only have a few topics, what does that mean? Yeah, there's a lot of questions on those few topics.
Oh.
All right. All right, chapter 2. We have the 3 kinds of cloud-based architecture. Host-based, client-based, and client-server. All right. Host-based was the first one, started in the 1960s with the mainframes, and it's centralized control, but it has a lot of problems. It can easily become overworked. Upgrades are expensive and hard. There are a few things that are good about it. Mainframes can have really big databases. And so if you want a really big database and you have a host-based cloud network, then you got everything's there, right? It's all on the mainframe. You got this huge database. All right, so we still use it. It's old, not as old as me, but it's old, and it is useful in certain situations, right? And then we have client-based, right? So client-based started in the 80s, and companies have tons of personal computers, whether they're Mac, Linux, or Windows computers. They have tons of these client computers, right? These computers that we normally think of as clients, right? And so this client-based has some advantages. The computers are easier to use, a lot easier to use than the mainframe. Let me tell you, they're a lot easier to use than mainframe. Mainframe does not have GUI. They have no mouse. Right? You have to do everything by the keyboard, and there's no pictures. It's really hard to use, right? I did it for decades, right? So it's, or at least over a decade. So it's very difficult to use mainframe. The PCs, man, they're a lot easier to use. Very user friendly. You got GUI to help you. You got the mouse to help you with the GUI. Software is much easier and cheaper. Hardware is much easier. So a lot of people use client-based, right? The problem with it is if you're saving data all over everybody's computer, it's kind of hard to get it all together, right? So it's very inefficient. And then client-server. Client-server, we talked about this a little bit a minute ago. Server is a very powerful computer that does one thing for thousands or millions of people. Clients are any kind of computer that are requesting services of that server. Normally, we think of it as a laptop or a desktop, whether it's Apple, Linux, or Windows. Right? Now, client server is much more efficient because you tend to have a database where everything's put together. Usually on the server, and you split the software. So the difficult stuff, the very complicated calculations and all that part of the software is on the server, the much more powerful computer. And then the simple stuff can be on the client. If you have a lot of simple stuff on the client, it's a thick client. If you have a little bit, it's a thin client. Right? Thick, thin client, and the server. All right, then we have the as-a-services. All right, first one is software as a service. A software as a service is where you're providing the hardware and maybe even some of the software, like your operating system and stuff like that, and the company that you're contracting with, cloud provider, they provide the rest of your software. And so your users would interact with the cloud provider and get the software through a browser, right? Like Google Docs, right? You get it through a browser. It's not installed in your computer. Right? So that is cloud applications, cloud software. And that's what software as a service companies do. Email, all kinds of stuff. All right. And then we have platform as a service, PaaS. So SaaS and PaaS. So PaaS is platform as a service, and this is where they provide the operating system and other system software, so device drivers and security utilities, antivirus, anti-spyware, anti-malware, all that kind of stuff. And occasionally they'll also provide a database for you. So your database will also be on the cloud with a platform as a service provider. Right? So you have a company and you don't want to deal with all of that kind of stuff, you hire a company that will provide those services to you. Platform as a service company. Right? And then we have infrastructure as a service, or IaaS. And infrastructure is hardware. Right? So infrastructure as a service, they provide the hardware. They provide the servers and the storage and the other network components. Right? The company is responsible for all the software. Now, they could be providing the hardware remotely, which most of them would probably do through the cloud, and you would just be installing your software on their hardware. Or they could, you could contract with them and they could put hardware in your data center and they would manage it remotely and all that kind of stuff. But you could get it that way. It's conceivable, but most of them are going to do it remotely. Most everything with these cloud services is via the cloud. Right, so it's not in person. So infrastructure as a service, they provide the hardware, company is responsible for the software. And then the last as a service, at the end of the chapter, is desktop as a service. And desktop as a service is a service where you create a desktop on the cloud and you add your applications, you add all your documents, all that kind of stuff. And then whatever computer you log into and you connect to the cloud, you see your desktop, not the desktop of whatever computer you're logging in on. You see your desktop that's on the cloud, and all your documents, even if you put them on the desktop or if you put them in the My Documents folder, all your programs, your applications are available to you, and you can use all of those. Now, this is really good for some companies because usually when somebody's laptop, somebody's business laptop, corporate laptop gets stolen, then the company is exposed. They're vulnerable. People can use their applications. They can maybe break into their network and all that kind of stuff. Well, with desktop as a service, all they have to do is give you a generic laptop, nothing installed on it. No software, no documents are on this laptop, just a kind of a blank laptop, right? Because it's just rudimentary stuff on it, like operating system, right? And then you log in there to the cloud and you see your desktop and you got all your programs and all your documents. Then when you log out, none of your programs and none of your documents are on that laptop. It's all on the cloud. So if somebody steals the laptop, they get a blank laptop. They don't get anything. Right? And so you could even log into the hotel's business center's computers, right? Or you could go to a client's office and log into one of those computers. And you have all your applications, you have all your documents, but when you log off, none of it is left on that computer at the hotel or at the client's office, right? So that's good security-wise. The problem security-wise is everything that's on the cloud can and eventually will be hacked. Right? Everything that's on the internet can and eventually will be hacked. So even cloud services are vulnerable to being hacked. Now, they've taken some pretty extreme measures to try to defend themselves, but the attack is better than the defense. And so if somebody really wants to, they can get in. All right. Then we have this. What's that? World Wide Web. What's the World Wide Web? A database. That's correct. What's in the database? Hyperlinks of where to find things on the internet, specifically web pages and the components of web pages, like pictures and video. The World Wide Web is a database full of hyperlinks of where to find things on the internet, including web pages, videos, and pictures. All right. Originally created by Tim Berners-Lee in 1989. Made it available free for anybody who wants to use it. Email protocols, got 4 of them. The email protocols, first one is SMTP, Simple Mail Transfer Protocol. Simple Mail Transfer Protocol is an outgoing email protocol. So when you send an email, you're using SMTP to send the email. Outgoing. Then we have 2 incoming emails where you receive an email. You have 2 incoming email protocols. We have POP, Post Office Protocol. This is the older one. It's one we used to use a long time ago, but it has some limitations, which are pretty severe. When the email comes in, it comes into the email server. When you log in, the email server downloads the email to your computer, whatever application you're using, like Outlook. When it downloads it to your Outlook, it deletes the email off the server automatically. Gone. Right? Now the problem is the computer that it downloaded it to is now the only computer you can read that email at. Because it doesn't exist on the server anymore. So the only one you can read it at is the one that downloaded to. So if you downloaded the email at your work computer, you can't read it on your smartphone, your laptop, or your home computer. Right? So you can see why we don't necessarily use this one as much anymore. Because we're more of a mobile society now, and people are checking things on all kinds of computers. Right? We still use POP, Post Office Protocol, but not as much. All right, so what we use mostly now is IMAP, Internet Message Access Protocol. Internet Message Access Protocol works the same. Email comes into the server. You log in, it downloads the email to your computer, but it doesn't automatically delete the email from the server. So the email remains on the server until you delete it. And you can make folders and all kinds of stuff. Put folders, this is my class for this semester, all that kind of stuff. Right? So that's what we use a lot now is IMAP, Internet Message Access Protocol. And the last one is MIME, Multi-Purpose Internet Mail Extension. So multi-purpose Internet Mail Extension is for attachments. Right? The email attachments use the MIME protocol. And that is chapter 2. All right. Just a few topics. What does that mean? A lot of questions. Yeah.
Internet
Message access protocol. Any other questions on 2?
What was MIME again, the acronym?
Multi-purpose Internet Mail Extension. IMAP is Internet Message Access Protocol. MIME, Multi-purpose Internet Mail Extension.
So 2 email protocols or SMTP and UP.
Those are for
SMTP
outgoing.
is an outgoing email protocol. DOP is an incoming protocol.
IMAP.
And so is IMAP. IMAP is also an incoming protocol. And then MIME is an attachment protocol. So those are the 4 protocols for email. All right, chapter 3. Modem and codec. Modems are for analog networks or voice networks. Codecs are for computer networks. Both words are made up of 2 other words. Modem is modulate, demodulate. Codec is code, decode. With code, decode, and modulate, demodulate. Now, a voice network needs analog data. So a modem converts digital data to analog for a voice network. Right? Converts digital to analog for a voice network. That's what a modem does. Codec is for a computer network, so it needs digital data. So it converts analog to digital for a computer network. Make sense? Converts analog to digital for a computer network. All right. Data flow. We have three kinds of data flow. We have simplex, half duplex, and full duplex. Right now, simplex is obviously the simplest. It is a one-way communication. You use this for radio and television. Right? It's one-way communication. You may love to sing along or yell at your sports figures on the television, but they can't hear you. Right? It's one-way communication. Right? Half duplex is two-way, but only one way at a time. Walkie-talkie. You press the button, talk, and say over, release the button, somebody else can talk. Right? Two-way, but only one way at a time. And then full duplex is two-way simultaneously. Right? Now, it's not like a two-way street. It's more like two one-way streets. Because you get a lot more throughput on two one-way streets than you can on a two-way street. All right, then we have multiplexing. Multiplexing is breaking one high-speed physical circuit into several smaller, slower circuits. Okay. Now, the reason we do that is we get a lot more throughput. Multiplexing is breaking one high-speed physical circuit into several slower circuits.
After that, so you get
Greater throughput, more data getting through. Right? Now we have four kinds of multiplexing. We have frequency division multiplexing, time division multiplexing, statistical time division multiplexing, and wavelength division multiplexing. All right, frequency division multiplexing. We're dividing the circuit horizontally, like a horizon, by frequency. So that's frequency division multiplexing. We do this with radio and television. We divide them by frequency. Right? The radios are different frequencies on the channel, and television, each channel is a different frequency. Right? So that is frequency division multiplexing. Time division multiplexing. We divide this vertically by time. So when you have more than two computers on a circuit, you can divide it up by time so that they can all communicate. Statistical time division multiplexing. We increase the capacity of a circuit by breaking it down into more using statistical analysis to break it down into the smaller components so we get more throughput, right? So using statistics to increase the capacity. That's where you may actually use statistics. If you ever do that. I took statistics in graduate school. I've never used it a day in my life.
Mm-hmm.
Not one. And I programmed all kinds of systems, never used it.
Good to know.
Never used algebra either. Never used any. I wrote financial systems. It's all addition, subtraction, multiplication, division.
What about the Pythagorean theorem?
Never used any theorem
Ugh.
in computers. Never once. Right? If you're writing a scientific program for researchers, you might actually use something like that, but that would be like 1 out of 1,000,000 projects. Right? Maybe one in your lifetime you would do. Right? It's not useful. Anyway, don't tell anybody I said that. So wavelength division multiplexing. Wavelength division multiplexing is tricky because it's 3-letter acronym with 4 words. Wavelength division multiplexing. That's a little tricky. I try to point out the ones that are tricky, just because they're tricky. So give you a little heads up. So wavelength division multiplexing, we use fiber optics, and we divide things by color, like the color of the lasers that go in the fiber optics. So we divide by color. Now, right now, we're pretty much using all red lasers, but we will be using more lasers as we go along. We've got red and blue lasers that we use all the time, right? We got red for CDs and DVDs. We have blue for Blu-ray, right? So we use red and blue lasers a lot right now. So if we started sending red and blue lasers down our fiber optic cables, we could double the capacity of that cable just by using another color. Now, there's 16.7 million colors in the RGB color model. If we could use even a fraction of those different colors sending things down, you can increase the speed of the internet exponentially. Yeah.
Out of curiosity, why can't we use more than just red or blue right now?
Because they're expensive.
All right.
It all comes down to money. Right? Is it worth the money to come up with another laser that's a lot more expensive than the ones we use? Right now, no, not worth it.
But like, I don't know, maybe the color of it, because I know different colors on the spectrum.
Yeah,
Like,
what I'm thinking now, this is just something I'm thinking. I don't think I've ever read this online or anything, but we can change a color of light. We can use filters and stuff to change the color of the light. So we could use a red laser and have filters and have 1,000,000 different colors that we could broadcast out of it. That's why I think they should do it, but they never asked me. So, but all right, we have guided media and wireless media. Right? Guided media and wireless media. Guided media is basically connected with cables of some kind. Right? That's guided. Wireless is obviously not connected with cables. Right? It's wireless. So the kind of cables we have in guided media are twisted pair, which is 10 pairs of copper wire that are twisted around each other. We have coaxial cable, which is a very thick copper wire, and it is still the most commonly used kind of copper cable in the United States because the cable companies lay down so much copper cable in coaxial cable that it's taking us forever to pull it up all out of the ground, replace it with fiber optic. And then we have fiber optic, which is glass, and it's the most secure and obviously the fastest. We can go at the speed of light, which is no longer 186,000 miles per second because now we know it's variable. It could be faster or slower than that. All right, and we get into satellites. There's 3 orbits of satellites. We have LEO, which is low Earth orbit, medium, and geosynchronous. Geosynchronous is where you see half the Earth at a time. They do that for weather. Whenever they do the weather, you can see all the weather systems and all that kind of stuff. You're looking at a geosynchronous picture. The medium level or mid-level, that's where most of the company's computers are. But the LEO is the most interesting and has the least propagation delay. Right? It's the closest to the Earth, and so it can bounce off the satellite and come back. It has the least built-in lag or delay. That propagation delay is a big problem with satellite communications. That's why gamers typically do not get a satellite connection to the internet, because it has a built-in lag that you could never decrease. Right? Now, we have another kind of problem with satellite. We have the attenuation problem. Specifically for satellites, we have a raindrop attenuation problem. Okay? And that is, attenuation is losing signal strength for over time and distance, right? Raindrop attenuation is losing your signal, whether you're uploading it or downloading it, when it goes through a cloud that has raindrops in it, or it goes through the rain that's actually falling. Either one will actually absorb part of your signal. And so not all of your signal is going to get uploaded, not all of it's going to get downloaded. Right, so that's another problem, another reason why gamers don't have satellite. Now, low Earth orbit is mostly used for research purposes, to study like deforestation and I can't think of the word, where the land is getting washed away. Erosion, thank you. We do a lot of studies and stuff like that with little satellites that are in low Earth orbit. Typically, the kind of satellites in low Earth orbit are about the size of a loaf of bread, or maybe even half a loaf of bread. So that's typically the size. Low Earth orbit also has a lot of communication satellites in it. Elon Musk has put up his constellation of satellites. I think it's called Starlink. Yeah, Starlink. So Starlink is up there to help people who don't have communications to be able to connect to the internet. So a lot of countries in Africa and Asia are pretty poor, and they don't have infrastructure like telephone poles with lots of cables everywhere. And they don't have all that kind of stuff, and they can't afford it. And so they can connect via satellite, have a satellite phone, be able to connect via satellite and connect to the internet, connect to the phone system that way. And so he's doing that. He made it available for the people of Ukraine when Russia attacked and cut them off from the internet. He gave them access to his constellation of satellites to be able to access the internet. Right? Yeah. One of the problems with low Earth satellites is you don't last long. They don't last long because low Earth orbit is actually a little bit in the atmosphere. Right? And so they get a little bit of drag from the atmosphere. At a certain point, there'll be enough drag that it will fall out of orbit and burn up as it comes back to Earth. Okay. Now, there's two ways of looking at our atmosphere in Europe. From an astronaut's perspective, it looks like a very thin blue line around our planet. When you're away from the planet and you're looking at the planet, it's a very thin blue line where the sun's reflecting off the air. And so you can see our atmosphere. It looks very thin. But if you actually try to go through it, it's pretty thick. It's a really thick atmosphere, right? And most things burn up before they ever reach the planet because our atmosphere is so thick and there's so much resistance that it gets hot. Trying to go through it, it burns it up, right? So satellites almost always burn up, especially the little ones. Now, when we made our first space station, it was the Soviet Union or Russia, I can't remember if it was Russia or Soviet Union, and the United States made one together. And it was just a temporary short-range thing, lasted for maybe a decade before we started building the International Space Station. Well, eventually that space station fell back to Earth and burned up. And almost the entire space station burned up, except a big lead line safe. The lead line safe had enough mass that it could survive getting through our atmosphere. And that landed somewhere, I think in Australia. Right? But most things will burn up coming into the atmosphere. All right? Now, our atmosphere compared to Mars has very little atmosphere. Right? That's one of the problems of going to Mars. They have very little atmosphere. trying to land a lander on Mars is hard because we've got to go really fast to get there, and there's not enough atmosphere to help us slow down. So we have to do all kinds of weird tricks to try to make it slow down fast before it slams into the planet at thousands of miles an hour. Right? The moon has no atmosphere. Venus has like 2 or 3 times the atmosphere we have. Now, they have a humongous atmosphere on Venus, which is why Venus is the hottest planet in our universe, not Mercury, which is right next to the sun. It's hotter than Mercury. It's 900 degrees on the surface of Venus because their atmosphere is so thick. It captures all of the heat from the sun and it doesn't radiate out into space. So our nights are cool because the sun energy that's come in radiates back out into space, right? Venus doesn't do that. It keeps everything. So it just gets hotter and hotter and hotter and hotter and hotter. Now, it's mostly a volcano planet. Almost the entire surface is covered with volcanoes, right? Because it's so hot. You actually have metal rain on Venus because the metals get blown up into the air from the volcanoes. It melts and comes back down as rain. Okay, it's weird. We actually landed a lander on Venus, but the atmosphere was so thick that the lander landed, took some pictures, and was crushed. Just crushed it like an eggshell. Right? We would not survive. There's nothing we can build that would survive on the surface of Venus. It's so much pressure. It's like being at the very bottom of the ocean. There's so much pressure. Right? It's even worse than being on the bottom of the ocean. Right? So anyway, that low Earth orbit stuff burns up when it comes in. It's not a big deal. Back about a month or 2 ago, Elon Musk put up about 100 satellites in low Earth orbit. There was a little burp from the sun, little mass ejection of sun material, and it knocked 30 of the satellites out of orbit. It's pretty tenuous, them being in orbit. All right, then we have transmission modes. Transmission modes is kind of weird. We have parallel, and serial. Okay. So serial is where we're doing things one thing at a time in a row. We can't start the second piece of data until the first one has gone through. So we send the first one through, we send the second one through. So obviously it's going to be a lot slower. Right? Now this works both inside computers and on networks. Okay. Serial, we're doing things one at a time. Parallel, we can do things like 8 at a time. It's like having an 8-lane highway instead of a 1-lane highway. Okay. And a lot more through. Right? Whether it's inside a computer or on a communication circuit. All right, and then Ethernet. So how does the Ethernet transmit data? Well, the Ethernet transmits data using the Manchester encoding type. So the Ethernet uses the Manchester encoding type. Now, Americans, we would normally say Manchester. Right? We like to pronounce every syllable, right? But this is named after a city in England, which is Manchester. Right? It's like locally we have a city called Lancaster, right? You know, a lot of people will call it Lancaster. But I actually did that one time to a citizen that lived in Lancaster, and they said, no, the actor is Burt Lancaster. The city is Lancaster. Okay, got it. But so we have, that's one of the problems with English. There are so many things that are the same when you look at them on the paper. But depending on the context and how it's pronounced, could be completely different. Could be a different word. Lead and lead. They're spelt the same. Somebody leads somebody, the bullet is made of lead. You know, they're spelt the same. Why do we drive on the parkway and park on the driveway, right? I mean, American English is just mind-boggling hard. And it's harder than the other Englishes. Our dictionary is way bigger than the other Englishes, British English, Canadian, Australian English, because our English is made of all the other languages combined as well. So we have like croissant, which is a French word. We have chaparral, which is a Spanish word. We have tons of words from other languages that we use all the time in American English. Right? Our dictionary is like twice as big as the British dictionary. It's very big. And we use the same words and they mean different things, right? So we say elevator, and they're like, what's that? Oh, you mean the lift?
Oh my gosh.
Right?
So
it's quite different.
the lavatory,
All right.
the bathroom, the restroom.
So that's the Ethernet uses the Manchester encoding type. Right? All right, now sound. An analog transmission of digital data. On the POT system, the plain old telephone system, we use sound because it's an analog voice network, right? So we have amplitude, frequency, and phase. Those are the three kinds of measures of sound that we use, and we modulate that sound, come up with different ways of modifying the sound, right? So amplitude is the loudness or quietness of sound. So sound is loud or quiet. Right? The volume of the sound is the amplitude. The frequency is the pitch of the sound. So it could be high, or it could be very low. And a low sound would be a little bit harder to hear over a long distance. Where a high sound is easier to hear over a long distance. So I have a 4.5 octave range. When I get sick, I can actually sing the bottom registers of the piano. I can actually sing that. Right? Now, pitch allows us to change the sound by changing the pitch of the sound. Phase. Phase is the direction of the sound. And modulating is just changing the shape of the sound, whether we use amplitude, frequency, or phase. We're changing the shape of the sound. So we have AM for amplitude modulation. We have FM for frequency modulation. And we have PM for phase modulation. And then we have a weird one, which is QAM. We'll talk about in a minute. All right, so amplitude modulation changes the height of a wave.
What did you say about pitch?
Pitch is the pitch is the changing of sound, whether it's a high pitch or a low pitch. Okay. So frequency changes the pitch of the sound. It's the frequency, or it's the register.
Pitch and frequency is the same thing, right?
I'm sorry?
Pitch and frequency is the same thing.
Close. It's they're not exactly the same, but one defines the other. Okay, so frequency is defined by the pitch. Okay, I didn't want to get into a big musical conversation here, but I used to be a singer.
Mm-hmm.
I sung for 40 years. I sung in Carnegie Hall behind backing up a major artist. I acted on stage in front of hundreds of thousands of people. I was not a computer person. I wrote songs. I wrote poetry. I've written short stories, novels. Right? I was a creative person. And I tried this computer stuff. It's like, wow, I'm really good at this stuff. And getting paid $75 an hour to do this computer stuff, right? So it's like, You can buy a bunch of pieces of bubble gum for that, right? So, if you're not necessarily a computer person, give it a shot. You may never know. You may be really good at something that you never thought of before, right? So anyway, so AM is the height of the wave. FM is the number of waves per second. And phase is the direction of the wave. Changing the direction of the wave. Phase modulation and changing the direction of the wave. All right, QAM. Quadrature amplitude modulation won't be on the exam, but quadrature modulation, quadrature amplitude modulation is just using splitting the symbol into lots of pieces so that you can get more through using an amplitude modulation. All right, that was fun. All right, bandwidth. Nothing to do with size of signal. Bandwidth is taking the lowest and the highest frequency on a circuit, and the difference between them, subtracting the lowest from the highest, the frequencies in between, is the capacity of the circuit. Those are the frequencies that you can send data through on. Right, so each frequency you can send so much data through. So the more frequencies you have, the more data you can send through. So that's the capacity of a circuit. Yeah.
I'm sorry. Say it one more time. So you say it takes the difference between
the highest and lowest frequencies, or the capacity of a circuit. All right. PCM. Pulse code modulation. Pulse code modulation. Pulse, like when you're taking your pulse. Pulse code modulation. That's the North American standard for sampling. Right, we talked about oversampling and sampling last time. Standard sampling is pulse code modulation for North America. That's Mexico, Canada, the United States. Right. And then finally, you have VoIP. Voice over Internet Protocol. All right. Voice over Internet Protocol. Voice over Internet Protocol allows you to make a phone call anywhere, anytime, as long as you want, for free over the internet. And you can do video conferencing. Basically, what we're doing right here with the recording in class is video conferencing. I mean, we could all be talking, but we're kind of doing more of a lecture than a conversation. But you can do that, right? That's voice over Internet Protocol. That forced all the phone companies to buy all the cable companies to be able to stay in business, which is why your internet service provider is most likely a phone company. AT&T, Verizon, Sprint. Could be Comcast. It's not a phone company. Or others. Now, one of the problems with VoIP is the 911 system, 911 system. They don't know where you are when you call from a VoIP phone. Same thing with the cell phone. They don't know where you are when you call from a cell phone. But a landline phone, they know where you are. There's an address tied to that phone number, the landline phone. So they know that's where you're calling from. But we can't do that with VoIP phones and the cell phones. Now, the cell phones, we can actually do GPS, and we can do cell phone triangulation, where you're looking at the cell phone towers that you can see and they can triangulate where you are and all that kind of stuff. So cell phones are a little easier. VoIP phones, you can't even do that. Right? And so it's difficult to figure out where somebody is with a VoIP phone. They're still working that out, trying to figure out how to be able to locate people with VoIP phones. And that. All right, any questions about chapter 1, 2, 3? Something I went by really quick you can get. All right, the exam, obviously next week. will be roughly 50 questions, all multiple choice, single answer, no multiple answer, no true false, no fill in the blank, no essay. And hopefully everybody will do well. Yeah. The Scantron, I think the announcement came out this morning, midnight.
882E.
It's the rectangle that's green or blue, doesn't care what color. All right, any other questions? Yeah. Yeah, slender one, not the whole thing.
The